Departemen Statistika IPB menyelenggarakan pendidikan tinggi bidang statistika dan sains data untuk menyiapkan lulusan dengan kemampuan analitik dan komputasi yang mumpuni sehingga mampu bersaing baik pada level nasional maupun internasional. Lulusan Departemen Statistika IPB disiapkan untuk mampu menerjemahkan permasalahan nyata dalam suatu bidang ilmu ke dalam konteks statistika dan sebaliknya mampu menerjemahkan hasil analisis dan kesimpulan yang ditarik secara statistika ke dalam bidang ilmu yang bersangkutan, serta memiliki landasan yang kuat untuk mengembangkan keilmuan dan atau mengikuti pendidikan lanjut dalam bidang statistika atau bidang lain yang memerlukan penguasaan metode kuantitatif yang kuat.
Departemen Statistika IPB mempersiapkan kami, para mahasiswanya, untuk menjadi data scientist yang handal. Di Statistika IPB, kami diberikan bekal mengenai cara mengambil data, menganalisis, sampai menginterpretasikannya. Karena pada sejatinya, semua hal di dunia ini menggantung data, tak terkecuali hal terkecil sekalipun. Oleh karena itu, dengan kemampuan menganalisis data, maka berarti kami siap untuk bersaing di segala bidang. Statistika IPB, there is no statistics without variance.
Departemen Statistika IPB merupakan salah satu departemen terfavorit di Institut Pertanian Bogor. Menjadi bagian dari Departemen Statistika merupakan salah satu pencapaian terbaik dalam diri saya. Pembelajaran yang diberikan di Departemen Statistika terus mengalami pembaharuan seiring dengan berkembangnya zaman, khususnya di era Big Data. Lulusan statistik memiliki potensi tinggi memasuki dunia kerja, because statistic is a sexiest job.
Good morning again, honorable guests, ladies and gentlemen. Thank you for remaining on the conference agenda until now, and we hope you have been enjoying yourself at the conference so far. Ladies and gentlemen, we now will continue our program to the plenary session 4. Before we go further to the session, the committee have a video for you as an introduction. Enjoy the video. Now, Professor Baldisyah Ahmad from University Malaysia Perlis and Dr. Agus Salim from University of Melbourne, Australia will share with us. And Ms. Rahma Anissa, Master of Science, will be the chairperson on this session. I will read her CV in advance. Ms. Rahma Anissa is an expertise in spatial modeling, data mining, and actuarial science. She is a lecturer at the Department of Statistics, IPB University Indonesia since 2015 until now. Her educational background, bachelor degree from IPB University at the year 2011, master degree on statistics from IPB University at 2014, and master of actuarial science from University of Waterloo, Canada at 2021. Ladies and gentlemen, now let us welcome Ms. Rahma Anissa. The screen is yours.
Okay, thank you very much, Ms. Sarah. And good afternoon, ladies and gentlemen. First of all, I would like to thank the committee for having me in this conference. It is such a great honor for me to be in front of so many inspiring researchers, academics, and every distinguished speakers, and also the presenters that are coming here today. Although we only meet virtually, but who knows, maybe someday we can meet in person and create a collaboration among us. Again, my name is Anissa, and I will be moderating this live plenary session. This is the fourth plenary session in this conference, and we will have two inspiring speakers today. The first one is Professor R. Badlisah Ahmad from University Malaysia Perlis, Malaysia, and the second one is Associate Professor Agus Salim from University of Melbourne, Australia. Before we start, I would like to inform you several housekeeping notes. The first one is that this session is being recorded and live streamed. And I would like to invite you to use the ICSDS virtual background. And also, I would like to ask you to kindly mute yourself during the speaker's presentation and activate your camera whenever it's possible. This plenary session will be divided into 3 parts, where the first 2 parts will be the presentation from our both speakers, and then the last part will be 30 minutes of discussion. So if you have any question, you may type your question in the chat box, or you may wait until the Q&A session and then raise your hand and you can ask the speakers directly. Now, please allow me to introduce our first speaker, Professor R. Badlisa Ahmad. He is currently a professor of computer system at University Malaysia Perlis, and he is also a professional engineer and professional technologist. And his specialization and expertise is in computer and telecommunication network modeling, embedded system design, and open source software. Today, he will present his work entitled Software Defined Network, or SDN, Network Service for Big Data Science. Now, without further ado, let us invite our speaker, Professor Badlisa. Please come forward to our virtual stage.
Assalamualaikum warahmatullahi wabarakatuh. Very good morning.
Waalaikumsalam. How are you, Professor?
Alhamdulillah, fine, thank you.
Okay.
So shall I share my presentation slide, yeah?
Yeah, please go ahead. And please let me remind you that you will have 20 to 30 minutes for your presentation. Are you ready to present your presentation, Professor?
Yeah, can you see my slide now?
Yeah, perfect. Okay, the time is yours, Professor.
All right, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Thank you, Miss Moderator, Miss Rahna, Anissa, and also my pairing speakers, Professor Agus Salim, and all the participants for ICSDS conference. Today, my talk is about networking technology, which I suppose also relate to data science and also big data. This is the evolution of technology, especially in networking, computer networking, where the implementation of big data or data science is being used to improve the system monitoring and managing the systems. What my talk is about the concept on how data will be used to enhance the computer networking, the traditional computer networking, to make it more efficient and also manageable. And I will show you about the new architecture of the software-defined networking and a couple of examples how this can be used. I'm sorry, the slide just wouldn't work. So let me, all right. So when people talk about data science, I think it is all related to what people have been talking about, Industry 4.0 or Industry Revolution 4.0. There are numbers of technologies which will be used in the future, and this will really transform how we work and how we implement things. So Industry 4.0 consists of, and shown in there, augmented reality, system integration, cloud computing, big data. I think this is where the conference is related on managing, on managing and using big data which is available, and also on IoT, 3D printing, cyber security, autonomous robots, and also simulation. These are actually the technology that force all of us to change and all of us to do things differently. So this is also part of digital transformations what we are having at this particular moment. So my talk will be on the bit of history of evolution of computer networks and how digital transformation changed the technology, and then the technology names as a software-defined networking. And I will show you the difference between the traditional network versus the software-defined networking and also advantages, a bit of history and how it works, and where the data science is being implemented in the system to enhance the network monitoring and management through network analytics and also artificial intelligence. And I will show you on the core architecture, the current network and application, and also look at how security of the network is very, very important, where the network analytics is implemented in software-defined networking. Lastly, I will talk about the readiness. How ready are we in terms of implementing or investing in this technology? And in the end, I will do the conclusions. So basically, the history of or evolution of computer network is actually started since 1940. And then it evolved to 1950 by having the military system called SAGE, 1960, and so on. So this computer network has been here for a long, long time ago, since the 1940. And then starting in 1965, where it is really pick up, the technology becoming mature, where in 1965 at MIT, the first wide area network has been established. And also the ARPANET since 1968 to 1970, which called Advanced Research Project Agency Network, where they use the packet switching networking to implement the computer networks. And then 1973, where Ethernet has been improved, where we see the voice over IP, and also in 1979, where the Tokyo the first 1G of network has been implemented in Tokyo, and where the 1983, you can see that TCP/IP for LAN and WAN has been implemented, and you see the progress of the evolution of computer networking has been constantly changing. And then you start to hear the Cisco product and other product which has been enhanced their product on 1996 to 2000. 2009, you can see the 10 gigabit Ethernet has been introduced. 2010 is 100 gigabit Ethernet, and 2020 there are systems where people already implement 1 terabit of Ethernet over optical fiber. So you can see the evolution of computer networks has been pushed by the application, by number of users, and also by number of applications which has been introduced in the internet. And it seems like it's not enough. Everybody wants to have more data, more bandwidth, and so on. So it is the computer network is the core of modern communication. Nowadays, we can't live without computer networking. In fact, now we are depending on this kind of technology. So the rapid advanced communication has been possible with the progressive or advancing computer network and the ability to implement statistic data and perform data science processes. So in the future, it is no more very simple networking where you just forward the data, but it is more on how data will be used to improve the system. So this is a bit introduction. You have heard about PAN, LAN, MAN, and WAN. This is the types of computer networks that have been used. And also nowadays, we always use the wireless LAN, WLAN, and also at the server part, they are SAN, and then they have EPN, and they also of WSN, and also VPN. So these are types of computer networks that has been implemented or used. So in human, we communicate differently. As you see on your left side of the slide, you can see how we interact with people. We send hi, and then the other person will say hi, and then you start pose the question, and then you reply with the answer. Similarly to computer network, where we have the web client and we have the web servers, and they communicate exactly the way that we are as a human communicate. So the most important thing, the most important protocol has been used until nowadays, since 1990s, we call it TCP/IP. So it's called Transmission Control Protocol or / Internet Protocol. It's a suite of communication protocol which are used to interconnect network devices to the internet. So this is the very important protocol that's been used, and it also specifies how data is exchanged over the internet by providing end-to-end communication that identify how it should be broken into packets, the addresses, where it knows where the data to be forwarded, to be transmitted, to be routed, and when it will be received by the destination. So when we talk about Industry Revolution 4.0, you can't run away from doing digital transformation because everything's changed now. The way we do mathematics also changed. Now we have so many tools available. There's no more using hands. We use computer to do analysis and so on. So similarly to computer networks. So in digital transformation, it really drives lots of new application, new businesses priorities. So especially it will also transform processes and the business model and how people do businesses, and also empower workforce with efficiency and innovations. And also when the personalized customers experience, where now we interact more frequently with the customers. I'm sure you have used this online shopping and so on, right? So these kind of activities really drive the way we do business. And of course, the new priorities raised in IT and also network complexity, where now in terms of mobility, the traffic going around in the network is getting more and more. In terms of mobility, people keep changing, people keep moving around. And in terms of IoT, Internet of Things devices, there will be around 28.5 billion network devices will be connected and also exist by 2022. And the use of public clouds, so huge, and then the huge data has been populated in the cloud. And of course, 90 to 70% of web malware will be encrypted to make sure that data is secure. So by 2020, it is expected around 125 billion devices will be exist in that time. So it means that more devices means more data will be generated. So how do this computer network cope with that? So the traditional networks, of course, they have some limitation because it has been designed since 1960 up to now. So there must be some difficulties facing with this kind of technologies. Number one is because it's unable to scale onboarding and segmentations. Because in this huge, massive network system, sometimes when you want to expand the system, it's quite difficult, especially in difficulties to identify. And if you want to group users, for example, if you have cameras, if you have human resource people, and also in terms of security, in terms of billing applications. So you want to group this kind of application in different ways. And also you want to group different kind of devices all connected together. So it is very difficult for the traditional networks. And it is also difficult to provide granular access privilege. Maybe you want to have some users to have a bigger bandwidth. Some might have lower bandwidth so that you can make sure quality of services to specific user access. So that's also very difficult for traditional networks. And also the difficulties or the challenges in protecting users and applications from threats. This is especially in security because the number of devices increasing, number of users increasing, there is also a security threat which need to be looked into. So for traditional network, these are some difficult or limitation. And also it's quite difficult to or it is unable to meet the demands of digital networks, because you need to set up the security and also to enable mobility. For example, once you are at one faculty and then you want to move another faculty, so how does the IP address change, and how can you enable the seamless mobility for the users experiences? And also, as mentioned earlier, the user device for how can it be done, or how can it be segmentized, and of course the security on how you access the clouds outside your campuses or your organization. So these are the things which limits the traditional networks. So so this, it can be done actually, but it is very, very tough, because 90% of network changes are still performed manually. That means you have to go to the devices and do the modification right to the devices. It is not centrally, because traditional network is more on the distributed kind of systems. So So it is quite difficult to maintain such a current situation of big data, the increased number of devices. So traditional networks is really not a suitable system which can be implemented now. So that's the reason why we need intelligent networks, where we use all the data available, and the data should be analyzed to give the better services in compared to the traditional networking. So the need of intelligent network in this sense is we need to have translation and validation, where we capture business intent and then we translate into policies, and we should be able to check the integrity. And also the changes should be done automatically. So where all the policies has been devised earlier, what kind of system that you want it to be performed, so it will change based on the requirement of the system that you required. And of course, in terms of link failure, I'm sure everybody has here, sometimes your network is down, you don't know whether the server is down or not. So if we need to have a system which can really monitor before any link failure happen. So the awareness of the state of the links need to be monitored intelligently. And also in terms of assurance and dynamic optimizations, because to make sure that users connected to the network are the users that you allow, and they have the exact privilege for them to access the network and to the system. So these are the needs why we need to change from traditional networking into a new network system, which is based on intelligent networking. So that's where they come out with software-defined network, or SDN, where it provides automation of network operation, control and management using software, and of course, using big data. I think as a data scientist, I think this is the thing where you can really use your knowledge to help make the system more acceptable. I'm sure this is first time for you to hear this, but now my people also confused when they say what is SDN. Some say it's open flow, the protocol, and some say it's a separation of control and data plane. Some say centralization of control plane. Actually, this is all the same thing. If you look at different perspective, as shown in the picture, if you look at the elephant, if you look at the tail, you look at a different way. So basically, SDN is overall of this, is all of this. And the advantages of SDN as the intention of to replace the traditional network is to provide automation for simplicity of the management, and also allows more specific defined policy, and also to do segmentation of the network, and of course to defend against security threats. And I think this is also one of the reasons, at least to lower the operating costs. We don't need many people to manage the networking systems. and we use software to do the optimization and hardware software and the hardware savings and reduce capital expenditure, cloud abstraction. So these are all the advantages has been stipulated for the current or the latest technology. So the change of traditional into this SDN has been started since 2004, which implemented or done by the research at the Princeton University. Only in 2008, the software-defined networking has been coined, where they introduced the NOx or the network operating system and also open flow switch interface. And by 2011, Open Networking Foundation has been created, which consists of 69 members to enhance this technology for the future, which consists of Google, Yahoo, Verizon, DT, Microsoft, Facebook, NTT as the board members of Open Networking Foundation. And they have Cisco, Juniper, HP, Dell, Broadcom, IBM as members. These are big companies who manufactured the networking devices. And I think in 2013, they have the Open Networking Summit, where they have lots of people talking about software-defined networking. So the origin of SDN actually is originated from OpenFlow, a protocol where they propose to be used to manage the networking system. And it is based on centralized controller. I will explain to you what I mean by centralized controller later on, because by having the centralized controller, as I said, you want to effective management of the system. They propose as a centralized controller to define the policies and to define how each of the networking devices works. So this allows easy programming to the system, and for example, especially or to change the routing policies on how the data can be forwarded to reach the destination in on the fly. And so these are the one of the definition of software-defined networking. Basically, SDN consists of three important items: the separation of control and data planes, the centralization of control, and of course the open flow as the protocol to talk to the data plane. So basically how it works. So this is the traditional networks where you have, have you heard of switches, routers? So these are the representation of the switches and the routers. So basically what these devices do is they have this application-based software, and also consists of operating system, and they are hardware to do the forwarding all the packets in the networks. So basically, all these devices, they have the function of forwarding the packet, and also they have some sort of what I say is like a brain to decide where to forward all the data which has been received by their neighbors. So the traditional network consists of the combination of the brain and also the task to forward the data. So they are all into it. That's why the traditional network is distributed. That means once you configure the device, it will do the thinking when you connect it to the adjacent router or switches. Once they receive the data, so they are able to think where to forward the data by themselves. So the key here is that the traditional networks architecture works independently and distributively. So this is traditional network. So what they want to change in terms of architecture is they want to split the brain and also the task to forward the packets or the data towards the right destination. So they split into three layers. The first layer, they call it the infrastructure layer. So this is how they communicate using open flow. And also they have the control layer, and also they have application layer. So there are three layers defined in SDN architecture. So this is like the comparison where you combine the function of forwarding the data or the packets and also the brain, yeah, the control plane. This is traditional. So the SDN, they split it into just the switches, and they split the SDN, they call it SDN or the controller, to split the brain of the device, the previous devices. And the communication between the controller and the switches is through the open flow protocol, a method of communicating between the controller and also the switches. So it looks like this, the switch will perform easier task, just do the forwarding. But then the controller will do a lot of thinking by looking at like the eagle view, you know, they see all how the devices are interconnecting, and then they, based on the data that's been collected, they are able to decide and send the signal to the switches on how to perform the data forwarding.
Excuse me, Professor, you have less than 5 minutes more for your
5 minutes.
presentation.
Okay, yes, okay. So that's how these devices, as an SDN controller, is used as a brain to implement the network analytics and also the artificial intelligence implemented in SDN. To give here, which has been available in the market, one is the Cisco and one is by Aruba. So Cisco, they use intent-based networking, or they call it IBN. So as I mentioned earlier, the traditional networking, they use physical, they have to configure physically all the devices. So intent-based networking proposed by Cisco, they have this centralized controller to do the configuration centrally, to do all the supporting and detecting and defending the application running across all the network. So first of all, you have to set the user input business. For example, the configuration that you want the network to behave. For example, if you want the network to have higher priority for video conferencing data, so we put it there as our intention, and then the intent-based system will have to extract and do the abstraction of the required intent and do the validation, and of course approved by the network engineers on that particular intent. Once it's been approved, then the SDN will do the network orchestration to generate and deploying configuration automatically to all the devices. So this is how Cisco company implement SDN by giving the name called intent-based networking. So this is how they interact with the networking configuration. They have the intent-based networking, and they combine with the software-defined network technology to provide intelligent-based networking. So of course they will use AI. I think this is where the data scientists or all the participants here can involve on how to make the decision and how to do the analysis to make sure that the network functions are at the optimized level, so that it will provide user satisfaction. So this is all because of the 4 V's of network data. I think you have heard this before. Some say there are 5: volume, velocity, variety, and also veracity. So that's the reason why this SDN is very, very important to fulfill the network requirement imposed by number of devices, especially in IoT, and also the use of media social data, which increase yearly. So this is a network analytics implementation by the Cisco. They call it Cisco DNA Analytics. So if you are interested, you can go to Cisco and look at how they implement this Cisco data analytics. And for Aruba network, they have their own system. They call it network analytics and in SDN, where they call it Aruba Network Analytics Engine, or NAE, which perform the the orchestration of the intent-based networking based on data collected to give the better performance of the network functionalities. So I'm going to skip this one. So for example, this is one example that where, as I said, the number of Internet of Things devices increased. So we need to manage it properly. So the constraint, as I said earlier, the traditional in terms of network management is very difficult. Intense use of network resources. Whenever there are changes of devices, you need to do it manually. So you have lots of difficulties or challenges, especially in fulfilling the IoT implementation. So with SDN, it allows the control plane and data plane to be decoupled. It allows programmable management of how they manage of all the IoT, and also the system allows how you can change the network policies using just doing the programming, and it allow user satisfaction in terms of the data used. So how it is? So the traditional without SDN controller, you just remove this one. But for IoT architecture based on SDN, they introduce this SDN controller to have the bird's view on how the system can be managed effectively.
Excuse me, Professor, your time is up. Maybe you could wrap up your presentation.
Right, thank you very much. So the issues is how ready are we in terms of changing this technology? So as reported in 2019, only 43% really ready with this. I think because of the capabilities of the people or IT departments. So in conclusion, I think due to these rapid changes of the devices, of the users, we cannot run away from doing transformations by utilizing the data has been generated, and this data will be used to improve the services, especially in these examples, the computer network from the traditional to the software-defined networking, to software-defined network to improve the responsive and also to better perform and manage the data in the network. So thank you very much. Hope you enjoy the talk. Thank you.
Thank you, Professor, for your insightful presentation, and especially it is highly relevant to what we have today since the pandemic started. Every company is forced to digitize their services now. And I'm sure everyone here are enjoying your talk, but due to the time constraint, we should move to the next section. And thank you once again. And for the audience, if you have any question for Professor Badlisa, please hold your question until the Q&A session, because now we will hear the presentation from our next speaker. Let me introduce Associate Professor Agus Salim. He is currently an Associate Professor at University of Melbourne, MSP-GH and School of Mathematics, and he is also currently part of Statistical Reviewer Board of Diabetic Medicine and Research Quality Steering Committee at Baker Heart and Diabetes Institute. And today he will present his work in collaboration with his team with title RUV3NB, Integrated Normalization and Correction of Unwanted Variations for Single-Cell RNA Sequence Data. Please welcome Associate Professor Agus Salim. Hello, Professor.
Yeah, hello. Can you hear me?
Yes, I can hear you.
Okay.
And yeah,
I'm ready, so I'm going to share the screen.
Yes, please. And please let me remind you that you will have 20 to 30 minutes for your presentations.
Okay.
Okay, anytime you're ready, please, the time is yours.
Yeah. Can you see my slides here?
Yes, I can see your slide, but could you please show the slide? Yes, perfect. Okay.
All right. Okay. Yeah, good morning all. I'd like to thank the organizer of ICSDS conference for inviting me as a speaker. And yeah, I mean, it would have been very nice if it happens physically in Bogor, and I could just visit, but it's not to be because of the pandemic. So we have a virtual session today. So yeah, Today, I'm going to share with you what me and my team has been working on in the last maybe 18 months to 2 years in tackling the challenges that we face with analyzing large volume biological data. Okay, so this is just the outline of my talk. So I'm going to talk about single cell RNA sequencing. So I'm going to introduce you a little bit into that world, and followed by introducing our algorithm that we propose to tackle the issue that I'm going to talk about, which is removing unwanted variation from this kind of data. And then I'll follow with some benchmarking using real data sets. Yeah, so I'm not using simulated data. They're all real data sets finished with conclusions. All right. So just like any other, kind of fields, there is also a big data kind of revolution taking place, or has been taking place in biology since perhaps early 2000. This is a graphic that shows you the cost of sequencing one human genome over time. As you can see, it was very expensive then in 2001 when the first human genome draft was completed. It cost about 100 million then US dollars. But around 2008, there is this technology coming in called next generation sequencing that replaced basically Sanger sequencing, and it's much cheaper. So by around 2015, you can see you can sequence a genome for about less than 10,000. So what has happened then is this opens a lot of avenues to a lot of people, lab, clinicians around the world to have access, okay, to afford, to be able to afford the sequencing technology for their research. So we've been dealing with a lot of sequencing data that's large in volume, but not only is large in volume, but also the velocity of the data. It's quite breathtaking. You can now sequence one human genome practically for 1 or 2 days only. Now the specific sequencing platform that I'd like to talk about today is called scRNA-seq. So that stands for single cell RNA sequencing. Okay, so the sequencing is done cell by cell. So the technology has allows us to do this. This is the typical workflow where, if the cells come from a tissue, obviously you have to dissociate the cells first, and then you need to isolate the cells one by one, extract the RNA, turn the RNA into cDNA for stability purpose. There is what's called reverse transcription process here, where not all the molecules that are RNA will be converted into cDNA. So some molecules will be lost, right? And the rate of molecule loss will be different from one cell to another. And then one way that people would do after that would be to perform from PCR. Okay, PCR amplification. So the cDNA will be amplified. Again, the PCR amplification process, the rate of amplification also different from one cell to another. Once you do that, you get this sequencing library. You can do sequencing, and then the data. Then after alignment, the data will be ready for analysis. For example, you can use it to find clustering of cells. So in order to identify cell types, okay. One thing that I want you to pay attention to, two things. Okay, the reverse transcription process here, where the rate of molecule loss is different from one cell to another, and the PCR amplification process here, where again, the PCR amplification rate is different from one cell to another. So at the end of the day, what happens is that when you have the sequencing count from each cell, okay, the relative counts may not reflect the original relative count here, okay, when it was in the RNA form, because of these two steps. Yeah, we'll come back to that and why it is an issue. Okay, so this technology has been used to discover rare cell types for immunotherapy. If you remember, in 2018, Nobel Prize was awarded for immunotherapy. It has been used for better understanding of cancer microenvironment and also understanding of neurological disorder. Okay, now we come back to the molecule count. So when you analyze this kind of data, the data molecule or rate count, okay? And there's a concept what we call the library size. So library size is just the total counts across gene for each cell, okay? Now, because of the reverse transcription process and the PCR amplification bias, this library size varies greatly between cells, okay? And it depends on biological factors, like cell types, okay, because obviously some cells are bigger. Yeah, if you have say epithelial cells, it is much bigger than immune cell like T cells. So it is naturally containing more molecules. Okay, but there are also technical factors that affected the total molecules that you see. Okay, and these are the capture rates and the PCR amplification factors. Yeah. Now, the idea is, people have shown that library size is a major source of variation in this kind of data. But the issue here is that not all of this variation are technical, but neither all of them are biology. Okay, so they are a mixture of biology and technical. Yeah. So the challenge here is we want to remove the unwanted portion that is due to technical factors, but we want to keep as much as possible variation that's due to biology. Sounds easy. I mean, people have tried. Turns out that it's not very trivial. All right. So how do you remove the unwanted variation due to library size? One model that people have used is to do a very simple normalization. So when I say normalization, it just means the step or the process of removing the library size effects. Okay, it has nothing to do with the normalization of having a kind of Gaussian distribution. So the basic idea here is to do a library size normalization for each gene. Okay. The basic assumption is that for each gene, the expected count that you have, okay, the expected sequencing count is proportional to library size. So you can see here, this is the expected value of count for gene G and cell C, okay? It is assumed to be proportional to the total, to the library size, okay? And if you take log, of course, you get this additive model. And the idea is that when you do library size normalization, you divide the count by the total library size, so that, at least in terms of expected value, you get rid of that dependent with library size. But whether this is going to work or not, we'll see. All right. So now, of course, I mean, people have departed from that kind of simple concept. Hafermeister and Satija from New York Genome Center, they use a negative binomial model, all right, where they model the count as a negative binomial random variable with a certain mean and gene-specific dispersion parameter. So this is their model, and as you can see, it's very similar to the underlying model that you have for that library size normalization, apart from the fact that here you have a gene-specific scaling factor, okay? While if you go back there, all the genes are assumed to have a scaling factor of 1. So this is an extension of library size normalization, and in general it works, but when we try this method, we are not completely happy with it, and that's what motivates our work. All right, so this is one of the motivating example that we have. This is 6,600 cells from non-small cell lung carcinoma tissues. This is sequenced only in one run, so there's only one batch performed in one day. Okay. So after we do library size normalization, you can see this the first two PC, okay, PC1 and PC2, and you can see when colored by library size, you can see that they're clustered by library size. Okay, there's the bright ones at the bottom and the not so bright on top here. Question is it bad? Does this really show that in our data, even after normalization, the clustering is dominated by library size? Well, we perform clustering using I think here we're using we use some kind of graph-based clustering. I can't remember the exact name here. We use 20 PC to derive the clusters, but I'm not only showing 2 PCs here. You can see we got 6 clusters. Okay, then we delve deeper. We look at the genes expression for this 6 markers. Turns out that each of these clusters actually represent different cell types. Okay, so everything seems to be fine because the one at the bottom here, they are epithelial cells. These are the green ones. Okay, and as I told you before, epithelial cell is much larger than the immune cells on top here, the monocyte, the B, and the T cells. And if you go back there, that makes sense, right? So this clustering that shows a kind of a clustering by library size actually biologically meaningful, because you would expect that the epithelial cells to be much larger in the molecule counts compared to the other cells. Okay, so at this stage everything is fine, but then we look at closer. So now we are splitting the PC now by cell type. And the idea here is that when you, okay, there are differences in the cell size, okay, between cell types, but when you stratify by cell type, I would expect to see that the PC does not have correlation at all with library size if we remove the library size effects very well. But what you see here, look at for epithelial cell, there is that gradation of colors. I mean, so there is still that library size effects remaining. Okay, you can argue there's a little bit there too for monocytes and perhaps for B cells. Okay, so this is the point where we said, okay, we can do better. We can do something. We can develop something better. Of course, that was more than 18 months ago, and we found it's not that easy. But finally, I think we cracked it. This is another example. You have 2 cell types here. So we know that there are actually 2 cell types here, right? 10,000 cells, about 4,000 and 6,000 cells each. But they are sequenced in 3 different batches. Now you can see that one of the cell type here is clustered together, okay? Regardless of the batch. The other one is separated by batches. So there's a clustering by batch for this cell type. It shows you there's a batch effect. So if you proceed with this kind of data and perform clustering, you will get 2 different clusters, 2 different cell types, while there's actually only one, okay? And that would constitute a misleading biology. So we need to do something to remove this batch effects. So here, the unwanted variation is the batch effects that we want to remove. All right, so going into my model, okay, my RUV3NB model, it's very similar to the previous model by Hafermacher and Satija, except that we have this term here. We have M beta, and then this the log library size has been replaced by W alpha. Okay, now let me tell you what W alpha is. W is the unwanted factors, the unknown unwanted factors. We don't know this. Okay, I don't pretend that I know this. I assume that I don't know it. I'm going to estimate that as part of my algorithm. Alpha is just the regression parameters associated with W. M is what we call the replicate matrix. So M is just a 0 and 1 kind of matrix where the number of columns equal to the number of subpopulations of homogeneous cells, and the number of rows is equal to the number of cells. Okay, now I'll show you later how we can identify this or estimate this matrix M. Okay, but it's very important. Our algorithm rely on being able to identify this homogeneous subpopulation of cells that we will use to identify or to construct matrix M. All right. So this is done within the framework of generalized linear model. All of those statisticians are familiar with generalized linear model with negative binomial likelihood, basically. All right. Now, because our data is so sparse, we also apply shrinkage to the regression coefficients and also the dispersion parameters. And of course, our objective is we want to remove the effect of W alpha from the count. And we'll see whether we are successful. Okay, so how do you do this? How do you estimate these parameters? Now, let's suppose we go back a little bit and we have a linear model rather than generalized linear model. All right, so we have this simple model here, linear regression. All right, if I apply matrix M into this equation, sorry, Rm, not M, so just the residual operator. This is a simple matrix algebra tricks. You will get rid of the M here. What is left is just Rm W alpha, okay, equal to Rm YG. If I put that in the matrix form, it looks like this. And all of a sudden, you see that if you perform singular value decomposition on this matrix here, you can write that as this term here. Then you can take this part here, the lambda multiplied by V, the right eigenvectors. That will be a good estimate for alpha. That will be one estimate for alpha. Okay, so you can estimate alpha that way in the linear regression framework, and then for estimating W, of course, we rely on what we call we take advantage of a control gene sets. Okay, so for control gene sets here, the assumptions is that it is not affected by biology. So beta is 0 for these genes. Okay, and we are lucky here. We have a very good negative control gene sets that we can use. I'm going to talk about that a bit more. So for these genes, because there's no biology, okay, beta is 0, you have this model, right? For a gene that come from that set. And if you know the alpha, all of a sudden, if you want to estimate W, you know, you just turn it into a regression problem where you treat W as the coefficients and alpha as the variables. Okay, so you get W alpha that way. Of course, that rely on two assumptions. Having control genes whose variation are mostly due to the unwanted factors rather than biology. And for this, we have a stably expressed single cell housekeeping genes that was published in 2019 by Ying-Sin, one of our collaborators. And second, the assumption is that we can identify subpopulations of homogeneous cells with similar biology to form the replicate matrix M. All right. Now, let's go back to the model. I mean, I spoke about the linear regression framework, but we have a generalized linear model. What do we do? Now, all of you are familiar that you can estimate generalized linear model parameters using iteratively weighted least square, okay, by iteration. And that's what we do. We perform an iteration where in in each iteration, we linearize the generalized linear model. We linearize it by performing first-order Taylor approximation, so that that model can be represented as a linear regression. All right, where this is just the working vector. Okay, and you can see this is now a linear regression as before. The only catch is that the variance now is no longer homoscedastic. The variance is now heteroscedastic. So in each iteration, you have to do weighted linear regression instead of linear regression. But everything else works. You can borrow that principle from the linear regression I just talked about. All right. So assuming that we can get the estimate of all the parameters, how can we obtain the corrected data? We propose something that's called the percentile adjusted count. So it consists of two steps. The first step is you obtain the percentile, okay, of your data under the full model that involve the biology and also the unwanted factors here, right? And then you get the lower and upper bound of that percentile, okay, and then just generate a random uniform number from that interval. Why you have to generate random uniform number? Because when you're dealing with discrete distribution like a negative binomial, you are not able to pinpoint the percentile exactly, and you only be able to estimate the interval where the percentile lies. All right. Once you get the percentile, you turn that percentile back into another negative binomial distribution. But now the mean of that negative binomial distribution, okay, still has the unwanted factors, but these unwanted factors do not vary anymore between cells. Okay, so it's like now you're having a constant unwanted factors, right? So we are not removing it, but we're making the unwanted variation to be equal to all cells. So when everything is equal, when you compare two cells, it's like there's no unwanted factors at all. All right. So the last ingredient is the identification of the M matrix, okay, because that's very important. Now, if we have single batch only, we perform clustering using what we call scan normalized data, okay, and declare cells in the same cluster as homogeneous and build our M matrix that way. If you have multiple batches, then you have to perform clustering for each batch separately, then followed by finding mutual nearest clusters across the different batches. Okay, and this is because you need to match the clusters so that clusters that you're matching have the same kind of underlying biology. Because when you're doing clustering, there is no guarantee that cluster 1 in batch 1 and cluster 1 in batch 2 are actually referring to the same cell types, right? Because clustering is an unsupervised kind of approach. And we also do an enhancement, okay? So both if you have single batch or if you have multiple batch, to make the cells even more homogeneous, we have this concept of pseudo cells that I can go through, but just want to check how much time do I have.
It's about 5 minutes.
5 minutes, okay.
Yeah.
All right, so I think I'll skip that the concept of pseudo cells. What I'm going to show you next is all right. So we do benchmarking of our method against SCRAN, SURAT3. These are all leading methods, okay, by very, very good people and published in Nature, PNAS, and Genome Biology and Cell, and see how our algorithm actually perform. So this is for the first data set. As you can see, we did not assume the W to be known, okay? And so we estimate our W, okay, where K is equal to 1. So we only have W1. And when we correlate that with log library size, there is a very good correlation. So what it tells us is that our method is able to detect that the unwanted factor is indeed log library size here, even if we do not assume to know that. This is the correlation between the corrected data from the different methods and log library size. You will see that if we remove the library size, well, the corrected data, at least for each cell type, should not correlate on average with log library size. You can see this is SCRAN, for example, for epithelial cell. There is a correlation there that is not zero. Our methods there, the ones that are a bit pinkish, that's very much closer to zero in terms of its distribution. You can see here also for the monocytes is the same. SCRAN is a bit off. Ours is much closer to zero. Okay. And you can see things like a method like ZimbiWave, although it's close to zero, but it has a very wide distribution. It's so overall we're quite good there. Here's the correlation between the PC, okay, principal components, PC 1, 2, 3, 4, and 10 with log library size. As you can see here, if you use only SCRAN, there's a high correlation with or R square here, which is the square of the correlation with library size, meaning that a lot of library size effect has not been removed. And here, if you use ZimbiWave, it's a bit better, but if you look at our methods, it's more yellowish, which means it's much lower. Okay, and we are basically competing with Surat acid transform here in terms of this metric. If you look at this particular metric, which is the silhouette statistics, we are much better. We are much higher, which means that our clustering by cell type is much better than other methods. And if we revisit that PC again, that example, you can see that if you use our method, you get a much better separation for monocyte. Okay, so that's that shows that our method is able to unearth the biology much better than SCRAN, for example. All right, so I'll just go through this very quickly. For the cell line data set, the second data set, remember that there is this unwanted variation in the form of the batch effects. Okay. When we apply our methods and get the corrected data, you can see that now the two cell types are clustered together. They are not separated anymore. So we remove the batch effects. And when we check, our W1 corresponds to log library size, and W2 and W3 indeed it's evident of batch effects. Okay. In terms of the metrics here. You can see that we are much better. It's very low. We are actually competing with SEmerge in terms of this metrics here for this data set. Okay, but where we differentiate ourselves from SEmerge is when we compare. So we perform differential. We're comparing the expression of the same cell type across batches. The idea is that if you remove the batch effects, well, then there should not be a gene that have a different expression across batches, okay? And we estimated that, you can see the green here, it's almost 1. That means all of the genes are not differentially expressed between batches, okay? And the other methods have a lot of genes that are differentially expressed between batches, showing that they haven't removed the library size effects very well. Sorry, the batch effects very well, all right? So this is just to summarize our methods against. So this is our methods against the other in terms of the different metric of performance. Okay, we have 5 or 6 metrics here. The fuller what do you call it? The fuller the sectors, the better the method. So you can see that our methods across the board are actually achieving a very good performance compared to some others. Okay, and this is, we also have result from other data sets where you can see that we are if we are not better, we are very competitive against the other methods. All right, so I'd like to conclude that removing unwanted variation while keeping biological signal is an important task. Okay, but it is very non-trivial. And we actually underestimated that when we started this journey. And secondly, based on empirical evidence, remember all of our data are actually real data sets, so we do not simulate. Our method actually perform these tasks better than current leading methods, okay? And we implemented this method as an R package. It's available on GitHub. You can have a look. The paper we hope to come out in a bioRxiv in about maybe a month time. And we are basically now speeding up the methods to be able to cater for hundreds of thousands of cells. And this last slide, I'd like to thank my co-authors, Terry, Ramya, Janan from Walter and Eliza Hall Institute here in Melbourne, my PhD students, Xiao Qi, who is extending this to single-cell proteomics, and Fahrul, who is working with metagenomics, and Alex Hayes, my collaborators, Alicia, Jean, and Yingxin. And we're also recruiting PhD students, so if you're interested, you can email me at this email address. And last but not least, I'll be forever grateful to Statistics Department, IPB University. I am the graduate of the department, and I'm very, very thankful for the department for laying the foundations to my statistics education. Thank you.
Thank you very much, Professor, for your inspiring presentation. And let's give us a big round of applause, a virtual applause for our both presenters today. And as we know that the RNA sequence data analysis currently is also widely used to develop the vaccine, and it can improve the vaccine development today so that it can produce rapidly, not like the previous. So as I said before, that the last part of the session will be the discussion. But before we enter the Q&A session, let me highlight some of the key takeaways from our amazing speakers. So the first presentation is from Professor Badlisa Ahmad. He explained about the evolution of the computer networking from traditional to adaptive intelligence-based system by utilizing algorithms and data and statistics to effectively manage and control data flowing network system. And for the second presentation that we heard just now from Associate Professor Agus Salim, he explained about the development of methodological advances to remove unwanted variations and normalize single-cell RNA sequence. And his proposed method is proven to be able to remove unwanted variation while improving biological signals simultaneously. And now let's begin our discussion. So for the audience that have questions for our presenters, for our speakers, please raise your hands and you can deliver your question directly to the speakers. Okay, is there any question from the audience or any comments if you would prefer? Okay, if no, maybe I have some questions for our first speaker, for Professor Badlisa. I'm just curious because you said that the SDN network can improve the security issue from the traditional network. Could you explain why is there can be more secure than the traditional networking? Maybe that's the first question.
Okay, thank you very much. Yeah, one of the important criteria for any network system is to avoid any security threat. So the traditional network is all depending manually by monitoring the traffic, by monitoring the users log into the system. So by using SDN, as mentioned earlier, it is programmable and it's automatically collect all the data, and the data will be analyzed by monitoring who's logged in, where they log in, and is there any suspicious activities that they've been doing. So that's allow how SDN proposed in advancing security threats, in avoiding security threat by using all the data collected to all the activities. So with proper analysis, SDN should be able to detect any potential threat, especially the users, the activities, so that they can block it immediately. So that's how software-defined networking, applying artificial intelligence in terms of doing analytic studies of the data, within the network to avoid any security threats.
Okay, thank you very much, Professor, for your answer. I will invite the audience once again. Please raise your hand if you have any question for our both speakers, or if you have any comments, or if you have similar research and then you want to share your research to our speakers, please don't hesitate, just raise your hands. Okay, I don't see anyone yet. Maybe they will still prepare the question, perhaps. Okay, maybe I will go to our second presenter, Pak Agus Salim. I just want to confirm, because I'm sorry if you already explained this in your presentation, but so is the process that you've been done here to remove the unwanted variation, is this process done in the part right after the PCR amplification process, and then after that you will continue with further analysis then?
Yes, yes. So this is very upstream. Yeah, I mean, so we do this immediately after we receive the raw sequencing count from the machine. This process needs to be done very early, because if you don't do this early, then all your downstream analysis may be compromised, right? If you have a bias like this, you identify them and remove them early, so that whatever you do in the subsequent analysis downstream, like clustering or differential expression, that would have much better kind of likelihood of discovering the real biology.
Okay, thank you so much, Professor Agus Salim. Okay,
there's a
we
question,
still have
I think,
time.
There's a question in the audience.
Oh yeah, thank you for noticing that. There is a question, right, from Muhlis. Question from Prof. Agus Salim. He is curious about the size of the predictor variable matrix, how many gene variable or features are used, and is there any risk that your proposed model will remove some important biological signals? And also there is another question, but maybe you will prefer to answer the first question first.
When we're talking about the genes, we are talking about before filtering, it'll be about maybe 20 to 30,000. But after filtering, often we're dealing about 10,000. Anything between 5 to 10,000. It depends on how deep you sequence. Okay, if you sequence very deeply, that means you perform kind of more kind of PCR cycles, then you get more read counts, and you can then analyze more genes, right? When you sequence more shallower, then a lot of genes will not have enough read counts, and they need to be discarded. I mean, I think the second question from the same audience is that whether my method has a risk of removing biology. Of course, I mean, any methods, have the risk of not doing what it's supposed to be doing. But that's why I think it's important every time you develop method, or even when you apply a method that's already developed, that you check using those metrics that I show that it's actually doing what it's supposed to be doing. If you and I've been guilty myself. I mean, in the past, that we just accept that the method will work. It turns out that it actually doesn't work.
Okay, so there is another question for Professor Agus Salim. It's on your slide 13. Could you please explain what the color represents once again?
Slide 13.
Yeah, it is. Okay. Question from Ashley. Yeah.
Yeah, I'll go back to slide 13, right? Okay. All right. Slide 13. I don't need to share the screen, I think. It's okay. So those colors, they are colored by library size. Okay, so the brightest the brighter colors refer to cell where the library size or the log library size in this case is actually higher. So you have more molecules for those cells, and yeah, more kind of less bright colors refer to cells with less molecules.
Okay, I hope that's answered the question for Asli. You can give comments on the chat box if you hesitate to.
Yeah, I'm happy to,
Yeah.
if you can email me, and if you want to have a further discussion, I mean, my email was there on one of the slides.
Okay, thank you for your answers, Professor Agus Salim. And I think we still have a few minutes left for this discussion. So I will invite the audience once again. If you have any question, you can type your question in the chat box, or you can raise your hands and then ask your questions directly to the speakers. So do you have any, is there any questions or comments? Okay, if no, wait, I have several questions also, actually. So maybe if there's no question from the audience, I will ask my question. Maybe I will go back to our first speakers, Professor Badlisa. In terms of the data science analysis, could you please explain briefly or about how's the SDN benefits us to do the data science analysis? Maybe it's related to the automatic data collecting or whatever. Maybe you can explain that. Thank you. I think you are still muted, Professor.
All right,
Yeah.
thank you for the question. Yeah,
Yeah.
the point I decided to give this slide is to make sure that all the participants, especially in the data science area, to know that within this area, computer network technology, you guys also has a lot of opportunities to get involved with. So SDN actually opened up more opportunities for all the data scientists to help to determine in terms of algorithm, to help how the networking system can perform very well in terms of the optimizations, in terms of do the services. I'm sure everybody is complaining about networking, right? Networking is very slow. Sometimes you say you pay with the amount of package that you pay to the telephone company high, but still the services is sometimes very low and very unsatisfaction. So this is where data scientists people will come forward to help these network technologies to come up with the ways to maintain the network, to make sure all users are satisfied with the services given, to differentiate between the higher privilege users and low privilege user in terms of making them satisfied in using the services. So this is where I think data scientists will help to provide better services for the computer network technologies.
Thank you very much for your answer. Just to confirm, so are we able to incorporate our algorithm into the algorithm that is flow in the SDN? Is that what you meant by your explanation before?
So far,
Okay.
so far the Cisco company, they have their customized system that allow you to import your algorithm so that you are able to see whether your algorithm is fit with the services required. Yeah, technology should allow us to use our own algorithm to help optimize or enhance the services in computer technology.
Okay, thank you very much for Professor Badlisa. And I think as much as we want to maintain this discussion, but due to the time constraint, again, we have to end this session. And before I end the session, let me summarize our discussion. So as we already as the both presenters explained before, that both of them explained the development or the evolution, but in the different fields. I think for Professor Badlisa, he explained about the evolution in terms of the computational network, and Professor Agus Salim explained the evolution in terms of the RNA data sequence analysis, but both of them works in a big data. So I think it is very beneficial for us, and we are lucky to hear their presentation today. And don't forget that Professor Agus Salim also mentioned that he developed he and his team developed his R package. So maybe for those who wants to use the methods, maybe can use the package and consult with him afterwards. And okay, and if you have additional questions, maybe if you didn't have any chance to express the question today, is that okay if they connect both of you through email?
Sure,
okay,
sure.
so yeah, you
it's
can
fine.
contact Professor Agus Salim and also Professor Badlisa through their email. And now we are reaching the end of the session. I apologize if there was any inconvenience during the sessions. And thank you so much for both speakers for your insightful presentation, and also for the audience for your participation during this plenary session. I hope that
Thanks
we
for
can
the
still...
organizer. And
Oh yeah, sure.
thanks, Professor Badlisa.
Yeah.
Thank you, Prof. Salim.
Thank you, everyone, also the committee, and I hope we can still connect to each other in the future. And please enjoy the rest of this conference. Have a good day, everyone. And I will hand over the session to the MC, Ms. Sarah.
Thank you. We thank you very much, Ms. Rahma Anissa, already lead the plenary session 4. We thank you, both distinguished professor, Professor Badli Shah Ahmad from University Malaysia Perlis, for your sharing under the title Software Defined Network Service for Big Data Science, and either to you, Associate Professor Agus Salim from University of Melbourne, Australia, for your sharing with the subject removing unwanted variations for single-cell RNA sequence data. Now I would like to invite Dr. Bagus Sartono, the Secretary of Department of Statistics, to deliver the token of appreciation to both Professor Badli Shah and Associate Professor Agus Salim, either to Ms. Rahma Anissa. The screen is yours.
Okay, so on behalf of the department, Professor Badlisa Ahmad and Professor Agus Salim, we would like to thank for your very insightful talk, and I think many people here got some inspiration from your talk. Okay, please accept our simple token of appreciation from the department and also from the committee of the conference. Here is for you, Professor Badlisa. Thank you very much again. We will send you the digital file of this token of appreciation.
Thank you.
Now, also for you, Professor Agus Salim, hopefully we will have a follow-up collaboration on the future, Professor Agus Salim and Professor Badlisa Ahmad.
Of course.
Okay, thank you very much. And last is also token appreciation of our department to Ms. Rahma Anissa. Thank you very much for conducting the discussion. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much.
Waalaikumsalam warahmatullahi.
Thank you, Dr. Sartono, and all of you distinguished persons. Ladies and gentlemen, we now will have an hour break time. Before you go, allow me to convey you 3 points as the program announcement. First, by 1 p.m. at Jakarta time, we will have our last parallel session. For the parallel session 4, still the same format, we need your cooperation to rename at your each screen. Room_session_name. For example, for me, then I will write 1_4_Sarah. The parallel session 4 will divide it into 3 rooms. Room 1 will discuss under the topic classification, either to room 2, and room 3 will discuss the topic time series. Please be on your each room on time by 1 p.m. at Jakarta time or in the next 60 minutes. Second point, after the parallel session by 2 p.m., we will also have our last plenary session. Dr. Hossein Ria Zoshams from Islamic Azad University Iran and Professor Lia Hemmerich from Wageningen University of Netherlands will share with us with their subjects. The third point, by 3:30, the closing ceremony will be held. Make sure that you will attend the closing ceremony as it will be a heart beating and session to know whether your name will call as the best paper, best presenter, or best audience. Thank you for your attention. Goodbye for now. See you again and enjoy your lunch.